Okay, now we've talked a lot about counting, the idea of counting things, counting principles. So now we're going to apply this and talk about our real goal, which is probability. So let's just start with something not too difficult here. Let's say we take a fair coin and we flip it 4 times. Fair coin just means there's an equal chance it comes up heads or tails, right? So one of the things when you're asking probability questions, it's nice to look at all of the possible outcomes that can happen if you flip a coin 4 times in terms of the number of heads, for example, that come up. And so the sample space, we use omega. That means you're going to list all of the events that can happen. And so one way to do it, you want to make sure you have all of the events, right? All of the possible things that can happen, and also not miss any and not double count any. So I grouped these in terms of the number of heads. So one option is you could get all 4 heads for your 4 flips. In this group are all of the ways you could have gotten 3 heads, right? They could have been first 3 heads and then tails, or the tails could have occurred on the 3rd, 2nd, or 1st flip. So there's 4 of those. All of these in this column are the number of ways of getting 2 heads and therefore 2 tails. So you try to come up with a way you can list, make sure you can get all of them. So I started with 2 heads, 2 tails. Notice I moved the rightmost head 1 spot over, and then 1 spot over again. And that's all you can do there with this first H in the first position. So then I bring the H's back together and then move both of them over 1 slot. And then same thing, I move that right H over. And then the last option is to move this left H together. So you have 6 of those in this column. Now, one thing to remind of, how do you know you have them all? Remember that we talked about the number in this column should be the number of arrangements of 4 letters where 2 of them are the same, 2 pairs are the same, right? So just like I had covered up here, we talked about on a previous video, the number of arrangements in the word data is 4 factorial because there's 4 letters, but you divide by 2 factorial since the 2 A's are indistinguishable. Here it would be 4 factorial over 2 factorial for the 2 T's and 2 factorial for the 2 H's. And that comes out to be 6. So you do have a way you can make sure you count all of them. Okay, continuing, this is all of the ways of flipping 1 head, and then no heads would be all tails. So if you add these up, 1, 4, 6, 4, and 1, you're going to get 16. Now, yet another way you could make sure you had all of the 16 possible outcomes, the number in my sample space, that's what this notation would mean, we can use the multiplication principle. Each blank here represents a flip of the coin. You have 2 outcomes for each flip, so the total number of outcomes should be 2 to the 4th power, which is 16. An example, we'll do some dice examples coming up, but say you were to roll 2 6-sided dice, or a single die twice. Each roll, there's 6 possible outcomes, so 6 times 6, you would have had 36 entries in your sample space. Okay. All right, but we're talking about flipping coins. Now that we have all 16 in our sample space, it's very easy to answer a probability question such as, let's let A be the event of flipping 2 heads. So the probability of A happening would be the number of ways A can happen divided by the total number in the sample space. That's our definition of probability. The number of ways of flipping 2 heads, we have them right here. That's 6 over 16 in my sample space. So that's 3/8. Okay, how about the event of flipping 3 heads or 4 heads? Okay, we were talking about when counting, if somebody asks for this or that, you would find the number of ways this could happen and add it to the number of ways this can happen. Well, in probability, it's a similar idea. The probability of flipping 3 heads or 4 heads means we want to count the probability of flipping exactly 3 heads and add that to the probability of getting 4 heads. And we can use our list here, our sample space. 3 heads, that could have happened 4 out of 16 ways. And all 4 heads, I'm sorry, I was pointing to the wrong column. 3 heads was this one, but that's 4 out of 16. And all 4 heads is 1 out of 16. So we get a total of 5 out of 16. Okay. Let's let C be the event of flipping at least 1 head. And we were talking about at least, when we were counting, at least 1 head means we want to count the probability of getting 1 heads or 2 heads or 3 heads or 4 heads. So we would add up those probabilities. We can certainly do that. We have the sample space. But we were talking about previously that anytime you have a lot of things to count up, you might consider the complement. And the complement of flipping at least 1 head is flipping no heads, right? You're either going to flip no heads or you're going to flip at least 1 head. Now, in the context of probability, the probability of getting no heads plus the probability of getting at least 1 head, since that's all that can happen in terms of heads, that has to equal the total probability, which is going to be 1, right? There's 16 possible outcomes. So all of the possibilities would be 16 out of 16, okay? So think of it as an algebra equation. The probability of getting no heads would be all tails, that's 1 out of 16. Probability of getting at least 1 head, which is all of these combined, let's just call that X. The total probability is 1. So if we just subtract that over, we get 15 out of 16 for our answer. Okay. So yeah, let's talk about dice, although in this case, I'm not going to be looking at the entire sample space, but let's say we roll a single, well, I guess I am, a single 6-sided die. A die is like a cube, has numbers on all 6 of the sides, 1, 2, 3, and then 4, 5, and 6. So your sample space I could just list as the set of numbers 1 through 6. Now we're going to define A to be the event of an even number that you roll, so a 2, 4, and a 6. And we'll let B be the event of rolling a multiple of 3, so 3 or 6. Another strategy for answering probability questions is to create a Venn diagram. Venn diagram is also kind of a list of all of your possible outcomes. But what's nice about a Venn diagram, you can probably tell right here that 6, the number 6 falls under both categories. Let me slide that back down. There. So with a Venn diagram, we can think of our whole world as inside this rectangle here. A, represented with this oval, is all of the even numbers, 2, 4, and 6. B is the multiples of 3, 3 and 6. So it makes sense to put 6 in the overlap between A and B, since that happens for both events A and B. Now 1 and 5 are not even or multiples of 3, so they would just lie outside the circle. Also, just to know that the probability of rolling any particular number, if it's a fair die, is 1 out of 6. You have a 1 out of 6 chance of getting a 1, a 2, a 3, 4, 5, or 6. And the sum of all those probabilities, of course, is 1. Okay. So let's say, what's the probability of getting an A? I'm sorry, of event A happening, meaning rolling a 2, 4, or a 6. And I kind of just said it, 2 or 4 or 6 means we're going to add those probabilities together. Probability of getting a 2 is 1/6 plus 1/6 plus 1/6. Probability of B, meaning getting a 3. Okay, another way to write or in set notation is with a union, a U. We know that when we do domains, right, in calculus. The domain is this set of numbers, union this other set of numbers, meaning or. So the probability of getting a 3 plus the probability of getting a 6 is 1/6 plus 1/6 is 2/6. Let me talk about this in a second here. That was kind of an afterthought. Okay, the probability of getting A, when you see an upside down U, that's read as intersect B. A and B, intersection and, both used interchangeably. So that's the probability of getting something that applies to both set A and B. And we saw the only number that that was true for was 6. So A intersect B is 6, and the probability of getting a 6 is 1/6. Right, probability of A or B means we're looking for the probability that you roll an even number or a multiple of 3. We've been associating or with adding probabilities. So we found the probability of A up here was 3/6. The probability of B was 2/6. But notice we're counting 6 twice because 6 fell in both sets A and B. And we don't want to double count this. So then it makes sense to subtract the intersection of A and B because we counted it twice in both A and B. And we computed the intersection was just the probability of getting 1/6, of getting 6, which was 1/6. So my probability then just becomes 3/6 plus 2/6 minus the 1/6 because we don't want to count that twice. That's why I went back up here. Anytime, so this is going to be our default formula. Anytime someone asks you the probability of A or B, we're going to use this formula. Now, if there is no intersection, like back here, okay, it was an A or B question, right? 3 or a 6. You can't roll a 3 and a 6 together. That can't happen together. So I put this in my notes kind of as an afterthought for this. This would be 0. So you don't have to have any intersection, right? And in fact, if there is no intersection, we call the events mutually exclusive. That's going to happen on my next example here. So let's just talk about this. So what's the probability of rolling an A or a 5? A is an even number. 5 is not even. So the probability of A we computed was 3/6. We would add that to the probability of 5, which is 1/6. And the probability of A intersect 5 would be 0. They can't happen together. So it really is just these two probabilities added together. So when that happens, when the A and 5 can't happen together, we call them mutually exclusive events, also called disjoint events. Okay, that's when two things can't happen together. Okay, let's talk about cards. Whoa, let's make sure we can see it. There we go. So let's say we take a card from a standard deck of 52 and we want to find the probability that we get an ace or a face card. Okay, so we'll define ace to be A, face card to be B. Remember, a face card is either a jack, queen, or king. And there's a jack, queen, and king for all 4 suits, for hearts, diamonds, clubs, and spades. Okay. So we'll use our default formula. Probability of A or B is the probability of A plus the probability of B minus the probability of A intersect B. There's 4 aces in the deck, so that's 4 out of 52. There are 12 face cards, so 12 out of 52. And you can't get an ace and a face card together. They're mutually exclusive events, so we don't have to consider the intersection. Well, I guess we do consider the intersection, but it happens to be 0 because they're mutually exclusive. So we would just add those together and get 16 out of 52, which reduces to 4 out of 13. Okay, how about a heart or a queen? We'll let A be the probability of getting a heart, B represent the probability of getting a queen. Now we should be thinking there is some intersection here, right? In our probability formula, we want to consider the probability of getting a heart plus the probability of getting a queen, but there is a queen of hearts in the deck, which would apply under both of those categories. So we're going to count it here and we're going to count it here. We don't only want to count it once. So we're going to subtract that out. Okay. There's 13 hearts in the deck, so 13 out of 52, 4 queens in the deck, and we're going to subtract out the queen of hearts so we don't count it twice. And that actually comes out to be the 16 out of 52 as well, which is 4 out of 13. Okay. What about the probability of picking a red card or a black card? We'll let A be red cards, B be black cards. Well, this one's hopefully obvious. The probability of A or B is the probability of A plus the probability of B minus the probability of A intersect B, which would of course be 0. You can't pick a card that is both red and black, right? So those are disjoint events. And what else is probably not surprising, that's what the whole deck is made up of, is red cards and black cards. So the probability of getting a red card is 26 out of 52, same thing for a black card. So those probabilities add up to 1. Okay. I know there are some problems that involve poker hands. One, what we call hand in poker, which is a hand is just a certain group of cards, of 5 cards that you get dealt in the game of poker, and we call that a hand. If you get all 5 cards are hearts, they're all the same suit, they're all hearts, that's called a flush in the game of poker. It's not important that you know that, but and that would probably be pretty uncommon, right? If you get dealt 5 cards, if they're all hearts, that's a little bit unusual, right? Now, how would we count that? Well, we need to know the number of ways of picking 5 hearts out of the 13 hearts. That would go in your numerator, divided by the number of ways of picking 5 cards out of your 52 total. I didn't work that out, but I'm guessing it's pretty small. What about the probability that all 5 are the same suit? Well, we just worked out the probability that they were all hearts right here. It would be the same probability for all being diamonds or all being clubs or all being spades. So we would just add these probabilities together. Since they're all equal, that's equivalent to just multiplying any one of these by 4. Okay, what's the probability at least 1 heart comes up out of your 5 cards that you pick? Okay, here's another situation. Okay, I hope you're realizing that this question gets asked quite frequently, where you could approach it by doing it this way. You could say, the probability of getting at least 1 heart means I could get 1 heart, 4 not hearts, or 2 hearts and 3 that are not, or 3 hearts, 2 that are not, or 4 hearts, 1 not, or all 5 are hearts. We could certainly do that, but that's going to take a little while to write all those down. Of course, the better approach in this case would be to consider the complement, which would be getting no hearts, right? So the probability of getting at least 1 heart would equal the total probability of just picking 5 cards, which is 1, minus the probability of getting no hearts, which is a lot easier to count. There's 39 cards in the deck that are not hearts. Remember, there's 13 diamonds, 13 clubs, 13 spades. That adds up to 39. We could pick any 5 of those and then divide that by 52, choose 5. Now, the idea of the complement, sometimes it's a choice. You have to decide if it's easier to compute your probability directly or using a complement. So for example, let's say we wanted to find the probability of getting at least 2 hearts out of 5. Well, what's incorporated in at least 2 hearts? That's 2 hearts, 3 hearts, or 4 hearts, or 5 hearts. So we'd have 4 probabilities to calculate. Or what's the complement of picking at least 2 hearts? No hearts, or 1 heart, right? And 4 that are not hearts. And so here you would only have to do 2 probabilities and subtract that from 1, which in my opinion, that would be faster. So we already computed that part on the previous question. Getting 1 heart means you're choosing any one of the 13 hearts, and your other 4 cards are coming from the 39 that are not hearts, right? These are not hearts. And of course, it's all over 52, choose 5. What if we wanted to do the probability of getting at least, I skipped one, at least 4 hearts? Okay. Well, at least 4 hearts really just means you're either getting 4 hearts or 5 hearts, right? So I wanted to show you, just so I don't want you to think that you always use the complement if they ask an at least question. You have to decide which is going to be easier. And here, I think it's easier to just compute this directly. At least 4 hearts means you're looking for the probability of getting 4 hearts or 5 hearts. And that's only 2 probabilities to add up versus the complement, where you'd have to do 1 minus the probability of getting no hearts, 1 hearts, 2 hearts, or 3 hearts. Okay, that would be a lot more difficult. Now, this idea of the complement is actually really, really useful, as you probably can tell. And there's a really, really famous and fun question to talk about, the birthday problem, that involves the complement. Say you had 5 people in a room, and you wanted to find the probability that 2 people in the room have the same birthday. Okay, that would seem very, very small. And in fact, it is very, very small that 2 people out of 5 people would have the same birthday. But how would you compute it? Okay, let's let A be the event of 2 people having the same birthday. That's what we're interested in. The complement of 2 people having the same birthday, which we can denote as A, like an exponent, A complement with a C there, is 2 people not having the same birthday. And it turns out it's easier to compute this probability using the complement. The probability of 2 people having the same birthday is 1 minus the probability of 2 people not having the same birthday. And how you would do that, okay, I put 5 blanks representing the 5 people in the room. The first person has a birthday, right? It could be any one of the 365 days, we'll assume non-leap year, out of the year. Now, the second person, we're looking for the probability they don't have the same birthday as this person, which means that could have been any one of 364 days out of the 365, right? Not this person's birthday. Similarly, the third person can't have the same birthday as either of the first 2, so they would have 363 out of 365 days to choose from, and so forth. So if you work this out on a calculator, you end up getting 0.027, which is very low, as you would expect. But an interesting question, how many people do you think you would need in a room so that the probability 2 people have the same birthday is 50% or higher? What's the minimum number of people? And maybe to set that up, think about this. How many people would you need in a room to guarantee 2 people have the same birthday? Again, assuming non-leap year. 366, right? If you have 365 people in a room, it could be very, very unlikely, but they all have different birthdays of the year. But that 366th person is guaranteed to have the same birthday as one of those other 365 people. Yeah. So we know that would be 366 people for the probability 2 people have the same birthday to be 100%. What do you think it would be? How many people would it be so that the probability is 50%? And of course, a reasonable guess would be half of 366, 183. It turns out it's much, much lower. If you if you run the numbers with the same strategy we did here, I made a little table here. If there's 10 people in the room, the probability 2 people have the same birthday is about 12%. Okay, and then it goes up 15 people, it's about 25%. And it turns out that the smallest number for which the probability 2 people have the same birthday just creeps over 50% is only 23 people. I don't know about you, but that really surprises me. And if you get 30 people in a room, it's about 71%, 40 people in a room, it's 89%, and 50 people in a room, it's almost going to be a guarantee, right? 97% chance that 2 people will have the same birthday. And this is a really fun thing to do. If you're watching this ahead of one of my classes, every time we talk about probability, I'd love to test it out. And it works almost all the time when I have even 30 to 35, 40 people in a class. Almost always 2 people have the same birthday, as the probability would suggest. So it's a really interesting probability. And again, it's a good use of the complement helping us to calculate a probability. Okay.